Welcome to the video lecture series for Texas A&M University, course Math 152. Today we will look at section 8.1, Integration by Parts. You can find the accompanying handouts at bit.ly/Raelene Math 152. Let's begin. We will start off by looking at some prior differentiation and integration techniques that we've seen. The first one, we want to take the derivative with respect to x of pi to the tan x. So we recognize that we have an outer function of exponentiation base pi and an inner function of tangent. So we take the derivative using the chain rule. And so for part A, the derivative with respect to x of pi to the tan of x will be the derivative of the exponentiation function. So it's pi to the tan x multiplied by the ln of pi. And that's the derivative of the outer function. And then we take the derivative of the inner function, which is secant squared x, joined by multiplication. So simply, if we want to reverse the process, we could imagine multiplying both sides by dx and integrating. Then the integral of the derivative of stuff, or the integral of d stuff, is just stuff. And we see the right-hand side is the integral of pi to the tan x times ln of pi, which is just a constant and could come in front, and then times secant squared of x dx. We notice that that's the expression we're starting with in part B, so the integral of ln of pi times pi to the tan x times secant squared of x dx must be what we started with in part A, namely pi to the exponent of tangent of x, and then because we have an indefinite integral, we need plus c, a constant of integration. And the technique that would be used here would be the integration technique to undo the chain rule, the derivative for compositions, namely the method of substitution. Now, if we hadn't just done part A, we would consider letting u equal one of the functions that we see here. We typically want to let u be the inner function. So we would consider u being tangent of x because it's inside the exponentiation function. From now on, we're not going to use u for the method of substitution. We're going to use t because we're going to be using u later on in this lecture. So with our method of substitution, we are going to let t be the inner function of tan x. And from here we can see that dt is going to equal secant squared x dx. Well, we have secant squared x dx showing up here, which will represent dt, and we have tangent of x being replaced with t. So therefore we would have the integral of ln of pi times pi to the tan x secant squared x dx would equal the integral of the ln of pi times pi to the exponent of t times dt. And from here we see that pi to the exponent of t is a basic integral, or a basic function with a basic antiderivative. And so the antiderivative of pi to the t is itself divided by ln of pi. So we get ln of pi times pi to the t divided by ln of pi, and then plus c, which leaves us with pi to the exponent t, which we back substitute as tangent of x. So had we not just done part A, we could have reversed the process of chain rule, derivative of a composition, using method of substitution. In number 2, fill in the blanks. So we have the integral of stuff dx is equal to f of g of x plus c. Well, if you didn't know the integral of the quantity here, you could take the derivative of the other side, and we know that the derivative with respect to x of f of g of x is equal to f prime of the inner function multiplied by g prime of x. And then we could multiply both sides through by dx, and we know that the integral of d of f of g of x, I have this is a square bracket and another square bracket, equals the integral of the right-hand side And here the integral of the differential cancels, and we're left with f of g of x, and then plus a constant can go on either side for the integration. So we know that this stuff must be filled with f prime of g of x times g prime of x, namely by the chain rule for composition, derivative of a composition. In number 3, determine the derivative with respect to x of the product sine of x times e to the x. Well, recall from Calculus 1 that in order to take the derivative of a product, we use the product rule. And so here we have the derivative of the first times the second plus the first times the derivative of the second. So if we just review that the product rule, d by dx of f of x times g of x is f prime times g plus f times g prime. We can apply that here. The derivative of the first is cosine x multiplied by the second, plus the first multiplied by the derivative of the second. By the product rule for derivatives. In part B, we are asked, what is the antiderivative of e to the x times sine of x plus cosine of x? Well, we can notice that our answer in part A is e to the x times the sum of sine x and cosine x, and therefore reversing the process, the antiderivative of e to the x times sine x plus cosine x must be sine of x times e to the x. And so we will always make sure with an indefinite integral that we include a constant of integration. So we don't actually have a method for performing this, and this is the nature of integration by parts. Just like we use the method of substitution as an integration technique to undo the chain rule for derivatives of compositions, we are going to use the integration by parts method as the integration rule that undoes the product rule for derivatives. So let's fill in the blanks. If we have a product f of x times g of x plus c, then its derivative would be something, or in other words, the antiderivative of something is the product f of x times g of x plus a constant. So what must be going in here is the product rule for derivative f times g. So we get f prime of x times g of x plus, and I don't have enough room to fill it in there, f of x times g prime of x. So integration by parts is the inverse of the product rule for derivatives. We are going to look at two different derivations of the integration by parts technique. Derivation number 1 asks us to let f of x and g of x be functions of x and to use prime notation. So to expand, the derivative of the product is the derivative of the first times the second plus the first times the derivative of the second. And then if we multiply through by dx, we are going to get f prime of x times g of x plus f of x times g prime of x, all multiplied through by dx. Then if we integrate both sides, we see that the integral of the differential will cancel, and that will leave us with f of x times g of x, and we can distribute the integral through on the right-hand side. So we get integral of f prime of x g of x, and we also distribute not only the integral but the dx from the back, plus the integral of f of x g prime of x dx. And then lastly, we are going to rearrange the integral with f of x and g prime of x. So when we integrate, or when we rearrange the previous equation for this integral or expression, we have f of x times g of x, and then we are going to subtract this term in order to isolate the green one, and so we get minus the integral of f prime of x g of x dx. All right, another interpretation of this without using the function notation f of x, we are going to let f be u and g of x be v. So we're going to use single variables to avoid having to use the function notation. So in derivation number 2, we repeat the steps above using Leibniz notation. And Leibniz notation says that u prime is equal to du by dx. And v prime is equal to dv by dx. So the first thing we want to do is start off by expanding the derivative of the product u times v. So d by dx of u times v is going to be du by dx times v plus u times dv by dx. The second step says to multiply both sides of the equation by dx. So we're going to get duv, so the differential of the product uv is equal to du by dx times v times dx plus u times dv by dx times dx. And we can see now that we can simplify the differentials by reducing the dx's on the right-hand side. So if we just rewrite that, we get d of uv equals du times v plus u times dv. And then we wanted to isolate the second piece. And so the second piece is this one. And if we isolate and rearrange, I may be missing my steps. We integrate both sides. I missed that step. So let's undo the box. We integrate both sides. And we can, of course, distribute the red integral on the right-hand side through the two terms. And then we want to isolate this term here in the last step. So we will have that the integral of u dv is equal to, well, we know that the integral of the differential will cancel, leaving us with uv. And we take this term to the other side, and we get uv minus the integral of v du. And so this is the very familiar integration by parts formula, that the integral of u dv is equal to u times v minus the integral of v du. And so it's a slight rearrangement of the product rule for derivatives, where we were starting off with u times v isolated. Now we're starting off with one of the other terms from the right-hand side being isolated. And this suggests why I didn't want to use the variable of u in the earlier warm-up question for the method of substitution, because we're now going to use u as one of the terms, or one of the original functions of the product in the product rule, as opposed to using u as one of the variables for the inner function of the composition. All right, let's take a look at some exercises. In number 5, we are given the integral of the product x cosine x dx. Because we don't have an inner and an outer function, or a composition, we are not inclined or wanting to use the method of substitution. We do see that we have a product, however, and so we are inclined to use the product rule reversal. In other words, the integration by parts technique. So just as a reminder, the integration by parts technique says we have the integral of u dv is equal to u times v minus the integral of v du. So what we need to do is align what we are given with the left-hand side of the product rule, or the integration by parts technique. So what we need to do is identify which term of the product x cosine x dx that we want to represent u, and which term or factor we want to represent dv. Well, there's really only two possibilities for u. We could either let u equal cosine x, and that means that du would equal negative sine x dx, and we would let dv be the rest of what is multiplied by cosine x, namely x dx. And therefore v would equal x squared over 2. We're not going to be using plus c's here. We will put a plus c one time at the very end of the indefinite integration. So we could use these four expressions to fill in the left and the right-hand sides of the integral. And if we did that, we would get that the integral of x cosine x dx, actually I guess what I've done is really rearranged it so that it's going to say cosine x times x dx where this is u and this is dv, is equal to u times v, so u is cosine x and v is x squared over 2. And this part has the integration complete. However, the next term on the right-hand side still involves making or working out an integral. So we have the integral of v times du. So we have v is x squared over 2 times negative sine x dx. And so altogether we have that x cosine x dx is equal to 1/2 x squared cosine x minus times negative is going to be plus, and then we have a 1/2 constant, and then we have x squared sine x dx. Well, we still have to work out this last integral, but we notice that it still involves a product. So we would have to maybe perform another integration by parts. But this first option is only one possible setup of the choices for u and dv. What's the other possibility for coming up with u and dv? So this is option 1. Well, given that we had x cosine x dx, if u is cosine x is one option, then the other option is u equal to x. So let's try that one. So the integral of x cosine x dx, we could let u equal x, which means that dv has to equal cosine x dx. And if u is equal to x, therefore du is equal to dx. And if dv is equal to cosine x dx, reversing the process of differentiation says that v had to have been sine of x. So now using our integration by parts rule, that says the integral of u dv equals uv minus the integral of v du. We have therefore that the integral of x cosine x dx is equal to u times v, x sine x, minus the integral of v du, which is sine x dx. So this is option number 2. And rather than trying to make sure you always get the right option from the beginning, you could just try. And once you set up the integral according to the integration by parts rule, look at the 2 results. We have a result here, and we have a result here. Which one, the green one or the red one, seems easier to integrate? Let's write the green one down again. We had 1/2 x squared cosine x minus a negative was plus 1/2 the integral of x squared sine x dx. Which of the 2 possibilities, option 1 in green or option 2 in red, looks like we can complete it? Well, because we still in green have a product, we would have to do another integration by parts to be able to hopefully simplify. The red option is more direct then, so we were going to go with option number 2. This is the more direct route for setting up u and dv to get something that we can integrate. So we choose option 2. The integral of x cosine x dx is equal to x sine x minus, and then the integral of sine x dx is going to be negative cosine x plus c. So the answer is x sine x plus cosine x plus a constant. And we are going to check our answer by taking the derivative. If we were to let this be y, let y be the function, therefore y prime is the derivative with respect to x of x sine x plus cosine x plus c. So derivative of the first times the second plus the first times the derivative of the second, and then the derivative of cosine x is negative sine x, and the derivative of the constant is 0, and we see that we are left with x cosine x, which is what we had in the original question. So we know that this answer is correct. All right, in exercise number 6, we have the same integral, but now it's a definite integral. We have the same integrand function. So we know that the integral of x cosine x dx worked out by option 2 as x sine x plus cosine x and we just have to introduce the definite integration bounds. And of course there's no plus c when we have the definite integral. Why is that? If you don't know, ask me. So we're going to integrate or evaluate now. We have pi by 2 times the sine of pi by 2 plus the cosine of pi by 2 minus 0 times sine of 0 plus cosine of 0. So we get pi by 2 times 1 plus 0 minus 0 minus the cosine of 0, which is pi. And so our final answer is negative pi by 2. We can take a look on the TI Inspire calculator to check to see if our answer makes sense or is correct. And so we go to the template, we go to definite integral from 0 to pi over 2 of x times cosine of x, integrated with respect to x. And we see a small mistake, so let's just go back and check to see what we did. When we were evaluating this, of course, I think I was thinking already of, I don't know what I was thinking of. Cosine of 0 is 1. Okay, so just go back to the cosine graph. And at 0, the cosine of 0 is 1. And so our final answer is pi by 2 minus 1, and we're happy with that. This number is greater than 0 because pi is approximately 3.14. Half of that is 1.57. Minus 1 is about 0.57. In number 7, we have the integral of x squared cosine x dx. Well, we had two options in number 5, and remembering that the integration by parts formula says that the integral of u dv is equal to uv minus the integral of v du, we have to set up an option for u and an option for v. So from the previous two questions, we found that letting u equal the polynomial term, the x, as opposed to the cosine x or trigonometric term, worked out for us. So we let u equal x squared, and therefore we let dv, because we're using the terms from the left-hand side, dv to be cosine of x dx. And therefore du will be 2x dx, and v will be the antiderivative of cosine x, which is sine x. So therefore we have the integral of x squared cosine x dx will equal u times v, which is x squared times sine x, minus the integral of v times du. So 2x sine x dx. And we see we still have a product here. So much like what we had in exercise 5, we had a product after the first option. But here I think we are seeing that the second integral is a little bit simpler because the power, or the highest exponent on the x, the power is decreasing from a power of 2, the second power of x, to the first power of x. And so this suggests that we are making the original integral a little bit simpler. However, it also suggests that we need to do a second integration by parts on the second integral. So the second integral, I'll put a box in green around it. And let's just focus on that integral. In fact, we're going to simplify it a little bit by taking the constant out in front. And we're really only going to focus on the integral of x sine x dx. So for the integral of x sine x dx, we are going to let u equal the polynomial term and dv equal the trigonometric piece, sine x dx. And recall that the trig functions have cyclical, at least for sine and cosine, they have cyclical derivatives and antiderivatives. So this is a very good option for the dv part of the integration by parts formula. Therefore, we have du is equal to dx, and we have that v is equal to negative cosine of x dx, no dx, just negative cosine of x. If you're not sure, the derivative of negative cosine x is sine x with respect to x. Now we can see that this is going to be a good option because the second integral of the green expansion is going to involve the integral of v du, and v du is a basic integral. So therefore in green we are going to replace the integral with u times v, which is x times negative cosine x, or negative x cosine x, minus the integral of v du. So minus a negative cosine x minus the integral of negative cosine x dx. Do be very careful with your negative signs here. So we get negative x cos x plus the integral of cosine x dx, and we can simplify that one more step and get negative x cosine x, and the antiderivative of cosine x is plus sine x, and then plus a constant. So we can take that and back substitute it in for the green box to be multiplied by negative 2. And so therefore the integral of x squared cosine x dx is equal to x squared sine x minus 2 times all of the expression above. And so negative 2 times negative x cosine x dx is positive 2x cos x, sorry, no dx there. And then we take negative 2 outside of the green box and multiply it by the sine x. And we don't have to call the constant negative 2c, we can just call it another c. I'm going to make it a bigger c, and that's a little c. So then if this is a function y prime should work out to be x squared cosine x. And I encourage you to double check that to make sure. In the next example, we have the integral of e to the x cosine x dx. Now, we saw in Calculus 1 how to generate higher order derivatives as formulas in terms of basic functions of e to the kx or cosine of x and products of these things. So we had to do some patterning. In the case of exercise 7, we had a polynomial term whose derivatives simplify eventually to some kind of constant. And it was that simplification or decreasing of the power from exponent 2 to exponent 1 to a constant that really helped us to get to the end of the integration by parts by performing a red and a green integration by parts. But in the case of e to the x and cosine of x, their derivatives never disappear. And so we will see a different strategy required to evaluate this. I'm going to keep taking the dv as the cosine x dx, so just writing my integration by parts formula, the integral of u dv is equal to u times v minus the integral of v du. And you should be able to see if you rearrange that this is the original f of x times g of x that has the product rule for derivatives. So we're going to let u equal e to the x and dv equal cosine of x dx. If this doesn't work, we can change it, and we can let u equal cosine of x and dv equal e to the x dx. And then we say that du is equal to e to the x dx, and v is equal to sine of x. So we substitute these in, and we get the integral of e to the x cosine of x dx is equal to u times v, which is e to the x times sine x, minus the integral of v du. V is sine x, and du is e to the x dx. So I'm just going to put the sine x in the middle. And we see that this is not a basic integral that we can work out, so it's still a product, which suggests that we need to do another integration by parts. So we still need to come up with, from the green box, we need to come up with a u and a dv. So let's let u equal, well, one of the things as a strategy that you want to use is consistency. If you choose the original integration by parts u to be the exponential function and the dv part to be the trigonometric function, stay consistent with that. Otherwise, you will undo the red step that you had just done and go back to the original. So we've decided that we're going to let the exponential piece be the u. So again, we have an exponential and a trig piece. Stay consistent with that. So the dv is sine x dx. What you could try to understand what I was talking about is to let u equal sine x and dv equal e to the x dx, and then see what happens when you apply the blue integration by parts formula with those different substitutions. Well, here we get that du is equal to e to the x dx, and v is equal to negative cosine of x. And so the green integral, which is the integral of e to the x sine x dx, is equal to u times v, which is e to the x times negative cosine x, minus the integral of v du, where v is negative cosine x. I'm going to change the sign, times du, which is e to the x dx. So we're going to get negative negative e to the x cosine x dx. And it looks like we're back to where we started from. But let's just see what happens when we make this substitution in the box here. So our red integral now says that the integral of e to the x cosine x dx is equal to e to the x sine x minus all of the green box. So that means we change the sign of this term and this term. So we get minus and negative is plus e to the x cosine x, and minus a positive is minus the integral of e to the x cosine x dx. Well, it looks like we've gone around in circles, except for the fact, because we've got the same integral on the left as we have on the right, except the integral on the right has a negative coefficient, which really means we can take that to the other side, where we find that we have 2 times the integral of e to the x cosine of x dx. And we saw this before with summation when we were using telescoping to come up with the basic integrals for I squared, I cubed expressions, etc. So here we see that we've got 2 times the integral that we originally wanted to evaluate or simplify, and it's equal to an expression on the right-hand side which does not involve any integration. So we simply need to divide by 2, and then remember, because we have an indefinite integral, there should be a plus c at the end. Now I notice that e to the x is common, so I'm actually going to factor out e to the x and divide by 2, and write my final answer like this. That says plus c. It's a little bit crowded. And so you'll notice that this is one of the examples that was in the warm-up, except we started from the product rule, taking the derivative of e to the x cosine x. Oh, except we did it slightly differently. We did sine x e to the x, but a very similar result. Okay, in number 9 we have the integral of sine squared x dx. Since we're dealing with the method of the integration by parts technique, we know that it is an integration technique for dealing with a product. So we should first recognize this as a product to say that it is sine of x times sine of x dx. We know then that we don't have 2 options for identifying u and dv, because we have sine of x and sine of x. So let's write our integration by parts formula. The integral of u dv is equal to u times v minus the integral of v du. And so we don't have the 2 options. We will let u equal sine x and dv equal sine x dx. And therefore we have that du is equal to cosine x dx, and v is equal to negative cosine of x. So we use these, plug it into our formula, and we see that the integral of sine squared x dx will equal u times v, which is sine x times negative cosine x, minus the integral of v du, which is negative cosine x times cosine x dx. So negative times the existing negative from the formula gives us plus the integral of cosine squared x dx. And so we see here that we've got kind of the same issue where we have cosine x times cosine x dx, and we would have to repeat the process. So if we do that, we would let, focusing on the green integral, and I think actually I will change the color of this to be red. So that in my green integral we have let, remember this is cosine x times cosine x times dx, let u equal cosine x and dv equal cosine x dx. Again, there's not a second option because cosine x and cosine x are the same when we switch them. So we get that du is equal to negative sine x dx, and v is equal to negative sine x, sorry, positive sine x. And so working out just the green integral, or the one in the green box, we get that the integral of cosine squared x dx is equal to u times v, which is cosine x times sine x, minus the integral of v du, which is sine x times negative sine x dx. In other words, negative negative is positive, and we have the integral of sine squared x dx. Okay, well, maybe this will become another one of those 2 times the integral examples. So let's take this green result and put it back into the green box so that our original red integral says the integral of sine squared x dx is equal to negative sine x cosine x plus what we found for the green integral, which is plus sine x cosine x plus the integral of sine squared x dx. And making sure that we haven't made any sign mistakes, we see that the negative sine x cosine x and the plus sine x cosine x cancel, and then in fact the integral of sine squared x dx on both the right and the left hand sides cancel, leaving us with a result that says 0 equal to 0, which is true. However, it does not help us to come up with an expression for the integral of sine squared x dx. So this does not seem to be a useful technique. What is a useful technique, however, is not to forget what we have seen in the past. And namely, that is all of the trig identities that we have seen. We can rewrite sine squared x using the double angle identity for cosine of 2x. There are 3 versions for the cosine of 2x expansion, namely cosine squared x minus sine squared x, or 2 cosine squared x minus 1, or 1 minus 2 sine squared x. If we take this third version then and rearrange, we can isolate for sine squared x. So this one says that sine squared x is going to be 1 minus cosine of 2x all divided by 2. And so using just basic trigonometric identities and no integration technique, we can rewrite this in basic integral friendly form. So we can rewrite this as the integral of 1/2 dx minus 1/2 the integral of cosine of 2x dx. Now, if you don't really see cosine of 2x as being a function with a basic antiderivative, you could do a method of substitution on 2x. However, we did learn in Calculus 1 how to deal with the antiderivative of cosine 2x directly. So we get the antiderivative is going to be 1/2 x minus 1/2 times the sine of 2x divided by 2, and then plus a constant. So the point of this exercise is to remind us that there are all of the other previous techniques that are still valid, not just the current one that we are learning. When we see the integral in number 10 of ln x dx, it looks like it's not a product, but we can still imagine that this product is of ln x times 1 dx. So ln x times 1, or simply ln x times dx. When we set up our integration by parts rule, we know that the integral of u dv is equal to uv minus the integral of v du. And so looking ahead, we want u to be something that has a derivative of du. Meanwhile, the dv suggestion or option that we select gets integrated. And so we have two options. We can either say we let u equal ln x and dv equal dx, or in option 2, we let u equal 1 and dv equal ln x dx. So just take a moment and for each of the two possibilities work out the du and the v. Maybe pause the video. Well, in the case of u equal to ln x, du is equal to 1 over x dx, and if dv is equal to dx, then v had been equal to x. In the second option, if u is equal to 1, then the derivative is 0 dx. Meanwhile, the antiderivative of ln x is, well, that's the whole point. We don't know. So this second option doesn't seem to be very useful, and we really only have one option. So let's go ahead and figure out what the integral of ln x dx is using the first option. U times v is ln x times x, or x ln x, minus the integral of v du, which is x times 1 over x times dx. And you can simplify x times 1 over x immediately. You don't need to write it down. And the integral of dx, well, the integral and the differential cancel, like we've seen earlier in the warm-up, and we're left with x ln x minus x plus a constant. Again, if you let this be a function called y, you should confirm that y prime is indeed equal to ln of x. Well, there are two more exercises. Number 11 says the integral of e to the square root of x dx, and number 12 is the definite integral from 0 to 1/2 of cosine inverse of x dx. Using some of the strategies and trying something when you're not sure what to do, I would like you to use these same strategies in number 11 and 12 and try them on your own. We will discuss these two questions in class, but I would like to see evidence that you have tried them on your own before class. Well, this concludes section 8.1. Please make sure that you have completed the handouts and prepared a list of clarifying questions about the lecture. That's all for now.